So let's start. Okay. I think that we can wait for some 3 to 4 minutes or 5 minutes, and we'll start today's session. You know, yes, good evening. I want to ask one thing. Till last week, any doubt and anything like that we can clarify and all. Today we'll extend that CNN session, and we'll take one example. Actually, that example is publicly available on that the MATLAB website actually. We'll take that example only and then we'll explain. So if you have any doubt and all, so till last time we can ask, and we'll wait for 2 more minutes. Then we'll start a session. So I'll just give the brief, like what are the things that we have done. CNN, like we started with the things that we went, and then the CNN we started. That is the first that's the machine learning model that we have started with that. And if we talk about, like, we could have started with that that supervised machine learning, or the like ANN, or maybe this SVM and all. But we'll talk about that in the last. But we have started with that. That's called on CNN. CNN, like, it's a part of deep learning, and we have seen that ANN also, like ANN will we didn't see much, but we'll go with that also. And it's similar to what we are dealing about the ANN and CNN. Only difference is there in the uh, neural that network will be having only one that the hidden that the layer will be there. But in the case of CNN or deep learning, we'll be having multiple that the layer will be there. Here, that's called hidden layer, or any other that's the layer one, layer two, that will be there. So that's the only difference that we have. Remaining thing will be same as it is, or it will be slightly difference will be there. And we have seen around that forward that propagation, also backward propagation also we have seen around. And we have seen, if we have a small number of data set, or even with for the ANN, we can go with the forward propagations and all. Once it will go to that's called deep learning. In that we have a different that the layer is there, and that layer will be different, 1 2 3 4 5. Like, as we are going to, we are doing the pooling also, and we are doing flattening also. Even today we'll see the transfer learning also. In the transfer learning, we'll see the encoder and decoder will be there. So what happened that our activation functions, or that activation functions or segment functions will be going to increase. So if you go with the feed forward that method, so because it's going to be a differentiation method, so it will take much time. It's easy only to calculate, but the thing is that what happened, it will going to comparatively expensive. Comparatively expensive will be there. So it will be, so if you go with the fit for models, it will be computationally that is easy only, but it will be more of a computationally expensive will be there. So we're not going much with that. So we are going with the that's called back propagation method. In that they're going to use chain rule that we have seen around it's if we have dy by dx, so we can go with the dy by a by da, like it's something we can go around. So that is the only one difference that we have with the two. That's learning method, and like then CNN we have introduced, and then we have that went through the CNN algorithm also. Different types of the algorithm we have seen around and all. So today we'll take one example, like we are going to do the train the CNN that model using that existing data what we have for the MATLAB in public, and we'll explain like how to recall the data set, or what should be the split wise, like some paper that so they're going to follow it up like 70-30 or 80-20, even some CNN or like a DL model, they're going to use that three cases, three split wise, like its first one will be the training, then testing, then that validation part will be also there. So that is also important part and all. So I think hopefully by today we'll end up with what you can say that CNN and all. So we'll wait for some more time, like 2 more minutes. If you have any doubt till now, we'll ask, just ask, we'll clarify and all. And I have updated all the like that my content in that like drive link. You can go and have access. I'll just show you. Mm. This is the link actually for drive link in that examples and all will be there. PPT also there, and then whatever the question we have solved. So all the questions are there itself. And still, if you feel like some need to be, so this is the sheet actually, so that you can get to the access if you are going to that dashboard, like the dashboard for the course actually. So in that problem solving session, and when you click on this, there is one sheet is going to open. So in the sheet, what will happen that for the both session, that for this particular course we have two different tiers are there to conduct the same, like same topic, same things will be solved, but it will be that actually if someone they were not able to attend the two-day session, so they can attend another session. And everything like they have like we have uploaded on the website, like on the YouTube actually. So if you feel like you're just lacking somewhere, so you can go into that YouTube also. You can get the access of that also. So this is the whole things that is the content that will be available for your full course and all. And if you want more of clarity, more of explanation, like this is the totally of a doubt solving session and all. And I'll suggest you, we have done two books are there. Like one, I have shown around one book, Deep Learning, with the Good Fellow. Good Fellow, if you go, so this is also publicly available books are there. So you can follow it around. So it will give the much basic clarity of that, and you can see around like how the things are working there. They have given that linear algebra also, and that optimization also. Then that machine learning basics also. Then they have started with the deep network and all, and like CNN all they have started all. Second book, I will suggest you to go through that pattern recognition using the Christopher Bischoff. What they're doing in that also, they have explained very detailed manner actually. So there's two book that you can follow it up. Other, if you still have doubt in this, you can ask me. I'll clarify in the class itself or in the session itself. And as we are going much Like we are going to introduce, like we have already started the CNN part. As we know that the CNN have like the input will be as an image. That image can be of anything. So once we have given the image, so we have checked around that like how they are going to do the indexing and all, like the feature mapping and all. So feature mapping and all that we have checked around the edges based, or they're going to make a segment and all. So we'll continue from there only, and then how they have done it. So now another topic is there in the computer vision, like we have the segmentation of the like deep learning or segmentation topic will be there. So segmentation we'll see today, like that is seen in segmentation and all. That's called semantic segmentation. We have two different types, three different types of the segmentations are there. That will also see, will explain to you, and we'll see like how based upon that also how a different model also came around, like that's called unet is there, and densenet is also there. So that came around, that the densenet we have seen around and all. So what happened, we'll give the input, too many input will that, so we're going to giving the as an image. So image is going to capture as a pixel. So what will happen, pixel they're going to capture. So there might be sometime like so they will able to capture full pictures also, like they have the feature map they're going to create. Sometimes what will happen, like the feature map will be not going to be like a very coarse means like very somewhere 1 point here, 1 second here, third here and all. So others, the other grid that we're going to make in the image, what will happen, they're going to create a dummy layer, like dummy features will coming into the picture. So to counter this and all that we came across, that is semantic segmentation we came across, like will whatever the feature we have the highest level of feature. So we're going to take it out, or then we'll go do up sampling or down sampling and all. Because once we are going to do, we'll take the feature from the input. It's that number of sample or number of the feature in the feature map will be the very high. So what we are going to do, we are doing in the first half, like we are going to do the down sampling. So whatever that irrelevant the feature, or maybe that's the first layer of the feature, like it's the starting of the feature, or maybe that's the low key feature. We're going to downsample, and once we go to the second half, after that hour we'll be having flatten. So we're going to do the upsampling. So upsampling, we will try to take as much as possible that the high like the impact the feature will be there, and then we'll come up with the whatever the classification feature will be there. The feature classification like output will be there. So in that also, in that context also, there is two terms in that name, encoder and decoder. That encoder will be the first half and second term. That will also see around. So now hopefully we'll go and start, and we'll start with the today's session with the like one simple like problem, like one code we'll be taking. I have already taken the code from the like that MATLAB website, and we'll explain the same code, and then how you can going to recall the code, and then how you can create and all. And we are not talking much about the how can we convert the image into the tensor or vector, because that we have seen already around like beforehand itself. Like we are going to take the grid, and then we are going to pros 24 by 24 or 28 by 28, or maybe 32 by 32 of, and then the channel, that channel will be like what is the source of the input that will coming around. If we have single pictures are there, so it's 32 by 32 into 1. So it's a single channel. And then we have taken for the gray color, we have taken one RGB value. It's called black and white. If it is going to be multi-channel, like three will be there. So like RGB will be there. That's called RG, that are going to stand for red. Then the green, then the blue will be there. Then we were having another types of that channel was there. That's the three dimensionals will be there. Like it's a advanced one. So we'll see one example. I'll take open the code itself. I have run the code also. We'll take the one code actually. So it's a simple structure of the code only. What we have to do, we have to create a data set. Like if we have the MATLAB, I have the MATLAB through the access through that my institute and all. And so you can see around that like we can go full will file, like they're going to create a full part to the MATLAB built-in digit data set. Like it's a already built in, like it's a publicly available also. You can see here also like how the things are going. Like it's Just search for train network for the image classification. The same have been explained by sir also. So this is here is the actually website you can see around. I'll just open this source file also. So actually, this example is actually for like that the handwritten notes was there. So we can see this is the how the handwritten notes was there, and a total of 10,000 synthetic data was that was actually stored in the form like 0 to 9 and all, and the image generated by using the random transformation to digit image, and it, like a different that font was there, and they have also classified like that's a 28 by 28 pixel that size. Even in our case that we can define by ourselves like based upon the RGB or the pixel itself, like we can say some that 32 by 32 or even 64 by 64, or even we have went through around the 256 also. So it based upon that how it going and all. So what they're doing, so they we have to load the data from where, like it's the MATLAB root, like it's in that there, and the toolbox is there, and then the demo will be there, the digital data like a data set is there. So if I'm going to do here IMDS, so you can see that they we can see here where it is there. So it's a file like where it is like it's a total of 10,000 is there. 10,000 data is there. So I'll tell you, like, if you're not familiar with the MATLAB, so we can like like it's good to have the that the MATLAB familiarity and all, but still I'll explain in some different way and all. So we can see around. So this is the toolbox, and this is the file is there where it saved actually toolbox nnet, like it's going to be a nnet means like it's going to be a neural that the network will be there. In that only we have like a demo is there. In the demo also data set different types of data sets are there. So this is actually example for the that's the image classification or the computer vision programs are there. So we can see they have labeled as a 00 till 9097, like that's the more categorical, that's the things are there. No? And what are the types of the file they have like going to support? So it's the TIFF and all like this is there. Okay. So there's a different types of the image source file is there actually. So once you're going to do like this, then after they will be going to show like what are the types of the data where label source is there. Okay. So then after like how many number of the data set will be there, that we can see just the total image in the data set itself, like display. Then after like from there it will come display numericals, and then IMDS, this is the source file. And then what we have, the files are there. Files we can see around here, like we were having the files also. Folder name and then files will be there. Okay. So then after like the second part of the things will be that like we have to like data set is there. Everything data set is there. So we have to see like how to that training or testing how it should, that how it should be done. So if in this example or in this that we have taken 70% image that we're going to use for the training, and 30% that we're going to use for the testing itself, like how to validate. In this, I didn't took the valid like what is it validation is not. If we have more number of data sets, you can do the validations also. So if so, then after they are going to IMDS train and IMDS test. So what we'll do, we're going to split each level. So again, what is the source file of that we can see on doc, and I want to see the split each level.
Sir, excuse me.
Yes,
Sir, I have a little query.
yeah, sure.
Uh, is there any standard golden rule? How much percentage of data can be taken for training, validation, and testing purpose, or it's depend upon data set?
It's going to totally depends upon the data itself. If I'll say in general, so we are following 70 to 30 or 80, that is a 80-20. And we know the 80-20 rule is this, that's also valid in this case also. But I'll say specifically, it's going to be totally depends upon the data set. Also, once you go for the one more term with there, it's called hyperparameter training will be there, like tuning of the model. So in that case, we play with this training data set, testing data set and all. So it's totally going to depends upon the data set only. And in general, if you're going to working on the ideal case, you take 70-30 and or either 80-20, both are okay. If that our results is coming good enough. Okay.
Okay, sir.
So we'll go see, and now we want to see like how split work and all. So in this all,
Also, you have here evenly split means what? Every
sorry,
digit class is evenly split.
every
First line,
or
split each
evenly
label.
split. Like I'm just trying to make sure that our data should be balanced. Let's say I have 10,000 data set is there, so it's a 10 part. So 1,000 data set for the like first class, one for one category, it's 1,000 again. So it's evenly split. Like I just
Okay,
try
they
to
are
make
not,
sure.
there is no skewed distribution.
Yeah, yeah, it is not skewed. Like it should not be imbalance.
Okay, okay. I mean, all are participating,
Yeah, yeah, yeah.
all members. Period.
Okay, for cross validation.
For this particular, we didn't did, but once we'll go for the tuning and also we can do the five-fold cross-fold validation or the grid search validations we can do it around. So that's again once we'll go into the that the more of the machine learning. Cross validation is something that we are going to in one fold we are going to that hold one set of parameters. Then again they are going to test on the another fold. Then something like this it will go like it's validation is something one will fix it out or one we are going to fold and we're going to train or test on the fold like full part of that. So cross validation is actually for the that's what the concept of validation come here. Only we have used the test and testing only, testing and training only. So if we need more robust results, so we can go for the cross-fold validations also. That we can go. Okay, so we'll go ahead with this. So there is again this data is actually it's going to be like balanced. There is sometime the things the data will be imbalanced. So the data imbalance we have to carefully handle it, or either we have to give the weight, or either we have to give some other parameter to handle the imbalance and all. If we are not able to, if we are not going to report in the paper like as a researcher or like we are working in that like academia and all. So once you write the paper and also we have to this thing that we have to clearly mention whether the data was imbalanced or not, or we have taken the data was balanced or not. If not balanced, so that we have to acknowledge in the future directions or maybe that limitations and all. Like the things can be balanced and all. So there is always going to be like a different way is there to that going to handle these problems and all. So one way is actually to provide the weight corresponding to that, so that the both the class or whatever that the class they are having that each that the balancing will comes into the picture. I think that so that the concept of the weight might be okay because the weight I'm speaking is something like let's say I have 10, others are having 7 only. So I have to become the proportionate of the 10. So I'll going to 7 into 1.33 or something like that. So that 1.3 will become the weight for particular data set. So it's become the for the both cases it will become the balance one. So weight means here like it's something proportion either to decrease or increase. Either we can bring down our data size to the whatever that like a small number that we have, but but this practice we don't follow. We'll try to go into like we can we'll go into that the use that the maximum number of data is there. Let's say in one class I have 100 and some classes that we have 70 or 80 is there. So that will not going to bring down the whole data set by interpolation or maybe the weighting and all to the 70. We'll try to keep the that so that the 100 one, and we're going to interpolate to the 100 others that what small numbers we have. So that's the one way that we have to follow it up. If you wish to bring down the numbers, there might be a chance that the model will not give the proper results at all. So then after it's again like randomized, like we have done splitting. It was not fixed. Like it's a randomized we have done. We like what is the concept or of randomized? Then the people will say no, 70% I'll take the data from the first to 1 to 7 and also it will become the bias. So bias will be more. So what will happen? It's going to underfit. Again, whatever the concept we have used till now, it's going to use it that the here also. So that's why we'll take randomize the functions is there. So they're going to uh, evenly or maybe they're going to take like that's a random way. They're going to categorize 70% for the trend, 30% for the testing. If someone is saying no, I'll go with first seven class, for 70% of the training, then 30 for the remaining for the testing. It might be chances for the bias. So bias, when the bias is more, it's going to be like that the variance will be less. Variance will be less. So what happens? It's going to be underfit. So this is how the things that we can call it for the training and testing also. So now we can see around what is the concept of the split each label. I told like it's going to IMDS is our going to be data set actually, and that point 7 is actually for training, and that we have used for the splitting how it happened. It's going to be randomized. We can see if you want to see some more fact about that how what is the concept behind the split each level or so just type documentation or just put the help, so it will come up. You can see it's the documentation came into. It's going to be valid for your what you can say that the MATLAB online is there. Okay, just split each level. So it came here. So we can see here. Split each level like description that IMDS be, then they're going to IMDS one and the two different types of the data set is there. Then they've taken the examples also, and then how it was done also. So that is one way that we can see around. Then we'll come to the architecture. Architecture is again going to be a very important part. As I said, like they have given the 28 by 28. That is what I can say pixel size. Left each digit image is a 28 by 28 pixel, and this is going to black and white. So it's going to be a single channel only. So it's a one with the one channel because the one channel because of the digits are in the grayscale image. So now we have to define if we go to the our that CNN that is going to layer and all. So three filter size of 3 by 3, and for each filter, so we have used 8 feature maps, and we have done for the padding also, and like 3 is the filter size, that the number of filter is the 8, and padding is again of the same size, 3 by 3 will be there. Then we have done with the relative activation layer is there, and in that also we have done the pooling also 2 by 2 of size straight of the second times second. So then after again the filtering again the second convolution that the layer start after the pooling, and but we have to start the second convolution layer also. We can see around here. Then after we have to give the training options also. We can give the training also. Okay, and once we define the after pooling, again the second layer started same thing, like 3 and 16. That's now the learning 16 going to feature map and all, and padding is also same. Then after fully connected layer also, once we are done with the pooling and all, so we can connect with the fully connected layer, and then we have the softmax layer. So softmax layer is actually they're going to convert any of the number into the probabilistic, like it's going to be a 0 to 1. So then after the classification layer, so again the question will come, what is the classification layer? So we can see it down here, the classification. classification layer. In that also that the layer will be there, the name and value, and then the name and output. Let's say that the name will be the like classes will be there, class widths that we don't have. Output size is going to again the auto. So what they will do 28 by 28 again same from there only it came. Seven one like that. So one is the image input, then 2D calculation, softmax, and then cross entropy function is there for the. Again the question become why cross entropy and all that I will again see around how it will go and all. So once it done, once we are ready with our architecture, first we have done like a data set we have divided, data set explain data set. Second step was to define the in and the scene and architecture. We have taken the only two layer like first convolution layer, then second convolution layer. Then after we came to the like fully connected layer, then softmax, then classification layer. That's going to output only. So it's going to compute the cross entropy loss during the training. So it's going to like it should be as much as going to low only. Then what we have, it's going to be training. Training, how we are doing training. So RDIM is also there, and then SDDM. I'll again show like what is the what types of the training that is we have optimizer or is there. So we'll go with the dog and training options. So that we have SDDM also, even we have the ADAM also, and other functions that also we are having. So in that also we have to give like what is that epoch will be there, what should be that our initial going to be a LR will be the alpha value we can say, what will be that dropout rate and all that we can see around and all. So it's something like it's a function or catalyst is there so that it's going to be like so they should show around. So I'll just show like how that our 1 minute layers are there. We can see here layers. So we have one as the image input 28 by 28 by 1. It's a 0 center normalization null. When we are using 2D convolution, like it's a 8 is the what we can say we were having the feature that map was there. 3 by 3 convolution was there with the stride rate of 1 by 1 and padding was the 001 like a single stride. Then we have used the patch normalization, then that ReLU function was there. Then that we have done the 2D max pooling also with the stride of 2 by 2. Then we have done with the batch again second came with the 16 feature map and then fully collected near then softmax classification output. So that the same thing we can see also that the print here also. Okay. Then after we'll go with the training. Let's say what are the options that we have. Options we can see here. We can it's going to be a gradient factor 0.9. It's a automatic, it's a predefined survey. Even we can play with this also. We can change the like that epoch also, epoch here 5 so we can put 20. Even we have the that batch size is 64 so we can keep around 128 and all. We can play with that also. So that max epoch also we can change around like here also. Then checkpoint frequency 1, then all the things that we need. Sometimes we don't need to pull like that the verbiage with the false. Like it's if something extra something like the wording is coming that keep as a false. Then after once it done, we are ready with the which optimizer that we're going to use, and we have we have made around CNN architecture also. So now we are going to train the CNN model. How we are going to do? It's going to train the model with the using a forward that the propagation is there, then the loss compression and then back propagation, then then the weight update. So now we'll check with the net. So we can see here that the layer and input as an image and output as a class image. So we can see this that the series network also in the documentation also. So it's actually series network is a neural so that's going to be an network and it's going to arrange one after one, and it has a single input layer and single output layer only. So this, so if anywhere you feel once you get through the code, either that you're getting the code that is already made, or you're going to write the code. So if you're feeling any difficulty, so either you go directly to that documentation. It will going to help it out. If not, if you want more some more clarity, that some clarity and all, so that you can follow the books and all, that will be always there. So then after, so what will be the test the train model? So what we have to do, we have to do the Y prediction, classify the net and IMDS test. We have already defined the IMDS test and all that we have already defined. Train, IMD testing and all that we have defined here. IMD train, IMDS test and all. So our Y prediction, it's going to be like what we are going to predict. Y test, it's going to IMD test that the label that is going to true label. Y will be the, it's going to be a that's going to be classify. It's going to be predicted one. So for the classification model, we have different types of that the performance matrices are there. One is the accuracy, second is the R1 precision score, the confusion matrices are there, and all are there. So we can see around. So for this problem, we are going to see accuracy. So sum of Y prediction, and it's not going to equal actually. It's going to operate only Y test by, it's going to be a numerical of the Y test and all. So then after they're going to display the test accuracy, and we are going to convert into that what you can say that going to 100, so that that become the 95% and all. Then confusion matrix again we'll check with the what is the confusion matrix, one the true positive, true negative, and all that. Once you go to the supervised machine learning, that will deal in the actual or maybe in the detail and all. So this is the whole code. We started with the what we started with the we have started with the like taken the image, and that image the properties we all know that it's going to be 28 by 28, but with the single gray and all. And for the testing and all, we have used the 70% of the image going to use for the training and the 30% of the testing, and that we have done the labeling also. Then architecture we have made. This parameter we can change around. There's no there is going to hard rule and all. I'm just taking one basics or simple example actually. And then after we have done the training Adam, actually it's going to that going to adaptive gradient method is going to update in each like layers and all. We can use the even the what you can say that we have seen one SJDM and all. Then after we have fixed around the that's the mini best size, and then verbose also. If we run, so there will be two things will happen. Once one another the tab is going to open it up. Hopefully it will go far. Just one second. It it depends upon the system. It will take some time that the less time also, sometime more time also. It came, so how the things it going to look like normally in the data. So two graph we can able to see, one will be the accuracy, that's going to percentage and all. Second one is the loss. Loss is going to be like let's see training loss and validation loss. As we don't have the validation here, so it's not going to be a, and we'll try to keep the loss as much as possible. We'll not try to keep like by ourselves. What we'll try to do, we'll make sure that our loss should be less, and then accuracy should be high. Once it run, So two things will come up, pop up. One will be going to a confusion matrix. We can see that the accuracy came around somewhere. That's the 98% means whatever the data division we have done that came good enough. And this is going to be a confusion matrix, predator class and true class, predator class. And we can see that the error is visibly less compared to the what you can say. This is going to class level zero, first class, second class, third class, fourth class. So we have divided into the 10 number of class, and we can see in this first and one to one we don't have any error, but second to first zero, we do have the error and all. So this is going to how it will look like the hour after once you run the CNN codes and all. So this is the one basic example that how the code structure will be there. Similarly, that you can take any that n number of example like this. So this is the one basic code that I explained here, and remaining that what you can see around, you can for any example you can see same structure, you can follow it up. So now this is the basic model. Now the things will comes into the like we can go with the parameter tuning. Like let's say for this basic result that so that the result going to came around somewhere how much. Um, 98%. So it's a good result actually. So here we don't need the optimizations and all, or maybe the tuning of the parameters and all. So once whenever we do the any biomedical applications like let's say X-ray or the MRI and all. So I think that you might have went across MRI that the tumor, brain tumor and all. So we can see the brain is will be the big of much size, like maybe like some big size will be there, but tumor will be visually very small size will be there. So what will happen if you're going to take a whole the things that it's going to make some the noise will comes, or maybe that unnecessary that is going to irrelevant data will comes into picture. So that time you have to either to reduce the sample size, or either to skipping the other parameter that we don't have that relevant of that study and all. So in that tuning that we have to do it. For this problem, we don't need to do the any tuning and all. We can go ahead further with it. So now, hopefully, this code is fine. Now we'll go ahead with we'll solve one problem like what is semantic segmentation for the like CNN and all. We can see arrow. So that we have seen around. Semantic segmentation actually nothing is going to be a make share. Like we are not going to find out the only. Just 1 minute. I'll take video there. Okay. So what we'll do, we are going to check around. Just 1 minute. So semantics, they're going to not just to recognize the what is the actually either whatever is the either the building, sky, or the fence, or the maybe vegetations and all. No, they're going to find out the pixel also. Pixel means intensity. Let's say if it is going to, if not able to find out the intensity, it might be give, let's say it's a 3D picture. RGB is there, but will not able to find out pixels. It's going to be like, will not able to get the accurate results. So that's why we have to semantize. Semantize something like we're going to click splitting the whole image and all. So segmentation actually is going to use in the computer vision task. So actually, and then it goes for the deep learning. And fourth, semantic like segmentation that we have, it's the total of three things are there. First one is that what we have is the instance segmentation, and second one is the panoptic segmentation, and then third one is the it's going to be a, like a semantic one. So we'll see what is the instance like image, what is the instance one. So image. So image segmentation actually what is that end-to-end image analysis. They're going to process the device digital image into the that's going to multiple segment and classify the information contained in the each region. Let's say I have one is there. This is going to be house. This is going to be cat, and let's say this is going to fence. This is going to wall. So semantics is something that we're going to identify each and every in the region, each and every that multi segments to find out that one. So for that we have three kinds of the segments that what we have. First one is the semantic one. Second one is the stance. Third one is the panoptic segmentation. It's just a theory. I'm just explaining it up. So once you are going to solve the problems, that you have to look around which one to use it actually. And most of the cases that we're going to use the that the semantic only. And if you go with the autonomous vehicle or even surveillance camera and all, so they're going to use the panoptic one. So panoptic one is something that we have to identify the object also, plus their look, that is the look alike, whether they are going to steady the sitting or roaming around, they are going running and all. So that we have to go to find. So let's say semantic segmentation labels every single pixel contained in the image by a semantic class. Instance and all going to use for the different classifications. Like instance is actually used for the multi-semantic class. Means that can be a entities or object. Like I told, like it can be an animal. It can be of people also, tree also, car and fire hydrants. It detects only the individual object or instance. And the output segment must a mask and is a specific identifier tag for the object. Let's say, so in this, what we're not going to, we are going to, like, let's say for the car only, I'm going to, that is the level one. Or maybe for the people also will make the level two. Something will do it. But in the semantic and all, what we'll do, we are going to find out the for each segment, we are going to find pixel also. Pixel, according to pixel, we are going to make the class also. But here, individual object itself make a class. And we have to mask it, because as we know that our machine learning model, they're not going to take any of that alpha part like as input. They need the only numeric. So we have to convert into, we have to mask a specific identifier tag for the each. In the in the panoptic, is something, it's a hybrid for the both. Panoptic is actually both semantic also, instance also. So in that both kind of information that we need to perform. Semantic segmentation also, so that our individual instance also. So in this, like it depends upon the where our application is going to use it or not. So why it is going to be important? It's going to help in the distinguish the different object class and object background region in the object. Let's say I have used CWT, correspondingly it came as calogram. One signal was there like this. One signal was there. Then converted into the one that FFT, like that they call histogram and all. Not histogram actually, it's called a scalogram. So what happened that in whenever we these signals are going to make signs, so there's some sort of some color and all came. But once it this reason, we don't have the intensity and all. So what will happen? I'll show you one picture actually. I have one work on it. I'll show you that how the scaleogram will look like. Scaleogram. Wait, I have. Actually, this is my work only, but I'll just show for the visual how will it look like. It will look like this. It is look like that. We have the EMG signal, and this one I took for only 1 second, and we have filtered it, like we have removed the noise and all. And once you convert it into the CWT scaleogram and all, so we can see around how like defined the things are there. So through the semantic one, we'll be able to see the intensity also. We can even with the classify also. So that's how the things with the intensity, we are going to define what I can say, like the pixel also. So that is the whole work it's going to do in the something called like panoptic and all. So semantic segmentation, they are going to make the help for the different object class and along with the background region in the image, like with the pixel also. So as we know that the AI or machine learning, that going to help for the recognition max play in the important for the training computers to they're going to help in the where computers and all. to recognize the context in digital image, like that's going to be a landscape, like it's whether it's going to morning photo or evening photo or afternoon all, then photo of the people also what they're doing, even with the intensity also we can see around, let's say as a sports person or the person who's working in the sport. So we'll take the picture once they didn't once they did not start the any activity, it's the one picture we took. Second picture we took once they have done mid stage of the training. So their facial will be going to change. Even the energetic then after the training, what happened? It fully tired. So that's again we can see around. Then the medical images, and then they're going to much more also we can see here. So it means like it's actually it's a computer vision problem. Computer vision problem actually. So it's going to give the machine to interpret visual information similarly to the human brain, while image segmentation models do share certain uses of the detection, like it's some other pixel also they'll give. Let's say, as a human being, we are going to give the visual information. Okay, they are going to be like tired, they are rest making, or they are like much okay. But the thing is that once you go into vision, so they're going to give the intensity of also, but like how intense that activity. Once we're going to define or once you tell the we can see the intensity also. So they identify different entities contained in the image at the pixel level rather than the approximate that information with the bounding box. So it means it's going to be like at the like very detailing way they can give it out and all. So how does that segmentation will going to work? Segmentation is going to be like going to get like segmentation map of an input image. We are going to, let's say I have this box is there. Let's say this is going to ball. This is going to be a others one B C D. So they're going to create a one like map, like how many types of objects are there, the corresponding intensity also we can see, we can see the corresponding intensity and all we can see phenomenon. So once it's done, so segmentation map is actually going to reconstructions of the original image in which each pixel have been colored coded by its segmented class, and we're going to create for the segmentation marks also. It's something portion of the image that has been differentiated from the other region. So that the masking is something like we are going to like one map will take and we're going to mask it. It's something that we are just making sure that segment is not going to come again or it's in the repeatedly and all. So let's say one for example is there. So it's in a tree, imprinted field without likely to contain three segment marks. One for tree, one for ground, one for the sky in the background. Let's say I have three are there. Here we have the field are there, and I'm just standing here like okay fine, and this is the sky. So how they're going to do? One mask they will create for tree. Second, they can create for the field where it's going to plant it out. Third one is the sky. So that's how the semantic expression is going to work it out. And corresponding each pixel is going to also define it. So just see how it will going to look like. So semantic, if we're going to overlay patch, so we'll take one object, we're going to run the CNN, it's going to building. Again, we'll take one segment, CNN building. Again take one more scene and then it came vegetation. It's but it will not going to make sense. Why? It's going to be very inefficient because we have to whenever we are going for the any of the that the machine learning problems and all, we have to do the work simultaneously, not the independent because all are dependent on each other. Let's say for the brain tumor and all, if we take one image is there, one tumor is there. And the thing is that we'll take this alone, we'll take alone this, but the thing is that what will happen, the accuracy might be not giving good. So there is no feature of sharing among development of the patches and all. So it's not we're not going to assume that one is not going to create impact on the others and all. So what have to do? So we have to do like we have to feature map. Then either do the up scaling, up sampling we are saying, or either down sampling we have to do. Then we I can go again try to retain the features and then we'll go for the output and all. How it will come? So first we can see the how the data set for the training. The task classified image data actually requires the data set considered of the pixel value, and that should be a for the mask should be there for the different object, and then that. So these are some data level that is going to publicly available. Let's say if you are having any data set, that's okay. Let's say you are going to the monitor in the like some factory, and you're doing for the first day, day one, day two, day three, day four, and you're taking the one picture, second picture, third picture, fourth picture, and also that sometimes the data set will be also available in the public also. That's one Pascal visual of the class MS Coco. They have around 330,000 images are there, and cityscapes are there, so that we can get for the urban environment and all that you can go, and you can run the CNN model also. So how the things will look like it's I'm just giving the one picture. It's inputted there. That's like their height and width. We'll be having some like 28 by 28 or 32 by 32 pixel and all will be there. Then the three channel we have. Then a conversion 1, 2, 3. Again, scores will be there. Then argmax. Instead of that here, softmax, argmax we're going to use. Argumentative max is something that is the whatever the value is there, there's going to argument. If you have studied the complex number, so argmax is something we're going to take the maximum of that. So maximum density. So whenever we'll say like in the normal symbol model that we can use the softmax and other that function we can use. Either we have to use the softmax only. But here in that semantic simulation that you have to use the argmax so that it will give the maximum probability and all. So this is the all things are same only. Only thing the argmax and then another things will be the up sampling and down sampling will be into the picture. So for the semantic segmentation, what we have that one, we'll be having different types of the that model will be there. We have seen in the CNN also we have the different algorithm was there for the CNN also. So here also fully connected convolutional that's going to be a network is there. It's actually a state of art of the neural that's going to be a network architecture used for the semantic segmentation that depends upon the several connected CN convolutional going to be neural that going to be a network. And if you see around, just then someone can ask like what is the difference between there and all. So in the traditional conventional CNN model architecture, made of the CN that layer and flat layer that going to be output single class level. But fully conventional that's going to be a network. They're going to replace some of those flat layer with the one by one convolutional block so that they can further extract the more information about the image. That's what we are saying upsampling. What's happened when we are going? We have the different type of features of that will more feature are there. CN1 conventional layer one and CL2 conventional layer block two. Then the things were the map size was getting decreased. Then flat layer, and then we were giving softmax, and we are giving the output class. But the thing is that flicker layer, we are going to give some of the flat layer. Let's say I'm going to use some 2, 3 flat layer. We're going to do with the 1:1 conventional block so that so they're going to do the upsampling so that so any information is there in that our feature that the feature map that got lost due to before the steps and all. So we'll be able to get it now. So avoiding the use of the flat dense layer in favor of the convolution, pooling, upsampling level max, so easier to train. So it's something that we're going to get the more and more information about the our features now. How the things will look like. What do you mean by upsampling and then downsampling? So as the network gathers more convolutional layer, the image size is going to reduce, as we have seen in the previous series that the CNN model and all. So for that case, what happened? It's going to less spatial information as well as the pixel level information will be there. So that process will say downsampling. If we go with the traditional, so that the forward process will go, it will become the downsampling. And at the end of this process, data engineer perform image optimization. Is something we are going to do the upsampling by expanding or upsampling the feature that's going to create a backdoor shape to the input. So it's something like we want to get whatever the size we given beforehand the feature map to get back into the original size. We have to do the sampling or image optimization. All. So if you're coming across with the both, so don't confuse with the image optimization and upsampling, both are same only. Then, as we know that what is that pooling and all, it's a tool in the process of that extracting information from the region of the image and analyzing them. Max pooling is something we are going to take. Let's say we have the 1, 2, 3, 4, 1, 2, 3, 4. So we'll take from here 4 will take. Then again, so this type of the box will be having n number will be there. So we're going to take 2 by 2. So from here max. Again from here it became 8. So 8. Again, so it will going to reduce from the n number of size to the m by n. Like it's going to be reducing size and all. So it means it's again like down something only, but the thing is that they're going to give maximum information. Like I told maximum pooling and all. So I think this thing we have seen around already because let's say this we were having a 4, 1, 3, 2. We took from here 4. Again we took 2, 2, 3, 5, 6. We took from here 6. And again, so it's simply this way we are saying the max pooling. So again, one more that first model is what the fully convolutional network that's called FCNs. Second one, what we have, it's a unit. Anyone have the doubt till now? FCN and all? Okay, hopefully it's all going good. So the second model what we have is the actually it's going to be called unit. It's an architecture modification of the original FCN. It's like extension of FCN model only. It was actually introduced in the 2015 to get the better results. It's going to consist of two parts, an encoder and decoder. I was speaking about what is the encoder, what is the decoder. The only thing difference is there. I will show you like what is the encoder and what is the decoder. Here, it's the encoder here. Then the flattening and wall will be there. So instead of flattening, we are going to introduce the one by one again the layer, then the decoder. Will explain to you. Don't. So while the encoder extracts the convolutional layer that are consistently downsampling the image to the extract information from it, then the decoder rebuilds the image feature. It's again same thing. Only but the thing is the term we have different is and in this one more thing is that whenever we don't have much like information about the image, so we're going to skip out. So one more feature is so that is talk in the second part. So first, while the encoder, what they're doing, they're going to consistently downsampling to image into extract the information from it. Then the decoder, it's rebuilding the image after the flattening. Instead of flattening, we are going to give one by one again the convolutional layer one day. Then it's called a process of deconvolution. Unit architecture is primarily used in the medical field to identify the cancerous or non-cancerous tumors in the lungs and brain. So whenever you see any of the the research paper, so there so the mostly they'll use the unit or we have the deep lab and the PSP net is also there that they are using it all. So this is a much bit of more information that I'm giving around. So I think hopefully once you're ready with the information or theory, so that you can apply anywhere or even that you can write the code also if you're good in the something I call the programming and all. If not, so I'll suggest you to just go through the packages. Package is something that is like deep learning toolbox is there. Then we have the machine learning toolbox will be there. Python toolbox are there. In that also Python and all they we have to write the code. But in the MATLAB we have apps will be there. We can see here machine learning is there, classification classifier is there, deep network design like designer is there. Then we have that NN fitting is there, clustering is there, then pattern recognition is also there. Then time series like it's to do CNN LSTM model is there. Regression model also there. So it's very important. Like simply just go and give the value in that instead of writing the code, you give the epoch value, you give the the number of neurons, epoch value or the learning rate. So and then input layer also. What is there? So that so the
Yes, sir. I have one question.
yeah,
How does it identify cancerous and non-cancerous regions in the
it's
brain or lungs? You said that this is used to identify
yeah.
cancer.
Actually, if we go, uh, it's an image based problem. CNN is actually they did the input as a image. Okay. So as we know that if you take the MRI, any of
Yeah.
the clinician or doctor, so they know that what is the exactly MRI will look like if a person doesn't have cancer. Okay. Let's say their intensity will be going to be same. Like like the pattern will be same. Okay. If any person, let's say it should not happen, but it any of the MRI was done and they took the image, but they have some miscom some like extra things are there. Like so that's called tumor in that in terms of that hmm, medicine, it's called tumor. So here patterns are clear. So it means it's going to be a non-cancerous. So it's going to class 0. Let's say if someone has a tumor, so we can that going to label as a class 1. Now we have to just classify using the CNN model. That's how they're going to use the CNN model. The only difference here is that we have to give the input image. That's all. I think it's clear.
Okay, okay. That
I'll
means based on the patterns,
yeah.
classify as
Mm.
tumor or not.
Yeah, yeah. Let's say I have segmentation here. Let's say brain tumor is there. MRI image will how it will going to link like. Let's say in this flare, like it's going to be an it's going to be a when someone doesn't have any of the what you can say like cancer is not there, but once the tumor got increases, so it become red, green or something. So it's the thing again it will go. So there's one problem with that we can work on it actually. MRI brain tumor from the MRI using deep learning models and all. So this is the one image, T1 image, T1C image. This is how the different types of the terming in the that MRI is there. So which one is going to cause the tumor so that the doctor will know. And we also know that okay, this is going to be this class, this is going to be this class. So we can just classify. Is it with the pattern?
Okay,
So in that also like what we have, but instead of we were dividing the convolution or deconvolution like encoder and decoder we have done, then we have the one more terms skip connection. It is actually important introduced by the unit is known as a disk connection used to connect the output of the one convolution. So they're going to use connect the output of the one convolution layer to the another one that is going to be non-adjacent. You see what we have one image is there. So we got one information from here. Second we have, third here, fourth we have, fifth we have. So let's say and whatever the output came from the one model or one that is that region came, So we're not going to connect with the another layer with the adjacent one. Instead of that, they're going to do with the fourth one or the fifth one and all. So that's called skip one. So that skip connection, what happened? This reason we have defined, this is also we have defined, this might be having same similar that the properties also. Okay. So this two segment, just 1 minute, wait, it went. Yeah. This two segment might have the same property. I am not saying it has that the same property. I am just going to assume it's have the same properties. So what we'll do, we're going to skip that one for hoping that they have that so that the same property, and we'll go with the here. So what we'll do, skip and connection process reduce the data loss during the downsampling, enable only higher resolution, means wherever we have the much more differences and all, so we can get the higher resolution output. And one more thing, they are going to have will if we don't skip, so they have to train or they have to run the model continuously for 1, 2, 3, 4, 5. But the thing now we can skip it out. We can get the best feature from here, best feature from here. Still, this is our assumption that we are making the code. We can play with that. That will going to run the code. That the result will come. Let's say that the result came 40% only. What happened? 40%. So again, we'll go back and we'll take second feature, then the fourth one, and something like we have to do to get the best features and all. So it's mentioned like it's so they're going to skip the adjacent that the layer actually, and so it's going to help to the reduce the data loss and downsampling, so we can get the better resolution now. Each conversion layer is going to independently unsample no upsample and combine the feature from the other layer until the final output accurately represent the image being analyzed. So it means each conversion layer is going to independently upsample, means like, so whatever sample we are going to each conversion layer, so we have to do independently. In the traditional method, what you do, we have to sometimes do the all together. Whatever it came, let's say I have one uh, this model is there. Till here it came downsampling came, then flattening came. So again, for all together, we'll do the flattening and we'll get the sum feature here, then output will get it. But here we'll do the again one layer, second layer, third layer, then we'll go with the again. So they'll do the independently so that it not going to left out any of the segment also. Okay, so in the unit, two things they're going to they're going to divide the whole architecture in two parts. First one is the encoder. They will do the downsampling. Then we have the decoder. They will do the upsampling. And one important part, they're going to do the skip connections also. So this is the whole about the unit. Then one more what we have, it's a deep lab. Deep lab is actually again it's all our computer vision problem only. Okay, so it was developed by the Google in 2015. Further improved on architecture of the original FCN, fully conventional that network, and then they're going to give the much more precise result. Like what they will do, so they're going to stack of the layer FCN, reduce the image resolution significantly. So what happened when we are going to first layer, second layer, third layer, so that the image that the resolution, or maybe what I can say, that the pixel is going to reduce. So significant architecture. So then deep lab uses a process called atros. So this is the one process. It's a atros. They will do what? To upsample the data with the atros conversion process. Conventional kernel can remove the information from an image and leave the gaps between the kernel and parameter. Let's say sometimes we don't have some info, so they were going to that's going to leave the info and all. So we have to think like, so deep lab they're going to use one process called atros, so that upsampling will do, and even they can remove some information from the image and between the kernel and parameters and also. How? Deep level is a dilation process. Dilation is something we all know that dilation is just something we're going to dilute one or two second layer or second, third layer, third or fourth layer and all. So pull out the data for the large page of the view while still measuring simulation. Like we have to take, we'll take the dilation. If we see the dilation, we have seen fifth, that is the fifth week. So we're going to do the dilations. But the thing is that output have will be having the same resolution. It's not going to change the output of that. So then it become feature space is then pulled through the fully created layer. Same again, same thing with a random field algorithm called CRF that we are going to use in the brain tumor and all brain tumor problem like MRI problem, you know. So more detail can be captured and utilized for the pixel wise for the logs function. So it will give the more and more accurate results. So this lab is actually they're going to do the dilation. Then after it will go through the fully connected layer with the random field algorithm. Like they're going to randomly go with the one layer, second layer, third layer, and all, so that we can get the each pixel with those functions also. Then they'll give the more clearer results or accurate simulation results. Then one more we have is the pyramid scene parsing network. It's again by the name itself, pyramid is there, and parsing is something like we are going to differentiate in all. So new segment algorithm for the segment was introduced. It's actually they're going to pyramid parsing model. I told pyramid type, and this is image dataset at a higher accuracy rate than its predecessor. So what they will do, they're going to gather contextual image dataset at a higher accuracy rate than it's the previous one. So, like its predecessor, like a PSP.NET, they employ the encoder decoder approach, but where deep lab applied upscale to mix like pixel level calculations. What happens? They're going to mix it up the unit also. Then they're going to mix it up with the deep lab also. Then they're going to do the multi-scale pooling so that we can get the wider range information from the it can put the other one. Unit is actually for encoder, decoder, skip connection. Deep lab is actually with the dilation with the address, and then they are going to use CRF model, CRF algorithm. So combination of both it came across the PSPN, PSPNet. It means based on the pyramid, for wherever the accuracy is more from the these two model, we'll take it and we'll do the multi-scale pooling again to get the better results in it. So I think that this is clear actually. Now we'll where it's going to use it out? It's going to use in the autonomous vehicle, self-driving car, or even that I told like it's going to be a biomedical applications that the CT scan, X-ray, MRI. Even with the farming also we can use it out. AI for automation for like detect infestation like that we can do it on we can like when we have to automate the spray of the pesticides and all. So we can do the continuous that the monitoring also. Now farming also becoming fully AI regulated now all. Even we can do with the photographic also, like landscape and all that can see around you. So now we'll see the transfer learning. It's again same thing we have CNN comparison of the economic layer, fully related layer, and even with that, what we were trying to do, like we have the input, then we have a conventional layer one, then cooling, again layer two cooling, then what we have straight of that, and then cooling came. Then is so this is that like baseline model. What we have. So what they will do in the fully connected layer, they're going to introduce the one by one like layers. Instead of flattening, we're going to introduce the one by one. So that what we have, we'll be getting the feature of 4096 to 40. main section. How it come? That will once we go and write the code, that we can get around. So how it would look like? Just see. So if you're going to so that the look around this picture, they're going to categorize correctly. We have 96 feature, then convolution layer one, two, then it become one by one, like fully connected layer. Then we came across the code. But the thing is that once we have the like different output is there, what happened? So it's become the codes. It become we're not able to give with here. We don't have any intensity in also. We're not able to give any pictures in all. What they will do? Subsampling that's why net reduce the output dimension to keep the filter small and then commercially coming on. Then the output are the cores reduced from the size of the input by a factor, like whatever the input we gave, and output came that the much lower that of that. So it means the bilinear interpolation is not going to work it out. So we have to introduce the fully connected layer, fully connected that network. How the things will look like here. Same thing is there. So now we're going to do with the semantic segmentation, that the segmentic segment. So that the one image is there, then the encoder is there. We'll be having that CNN batch utilization, and then the relu we have. Then the polling will be there. First, second, third, fourth, fifth. Then what we'll be having is going to be upscaling, upsampling here. One by one, we're going to introduce. One by one, we're going to introduce. One by one, we're going to introduce. Then the final decoder, then the output. So this is the input we have, and this is the output what we have. So if you want, so you can go and read this paper actually. Segment like a segment, a deep CNN encoder decoder architecture for the image segmentation center. So that's why to keep high frequency detail intact by using unpooling method. Unpooling method is something we're not going to pull it down. It's something we'll do the unpooling. How it will look like. Unpooling is something what we have from here 6, 5, 2, 9 came. So the 9 is there with me. From here 8 we have 8, 4, 1, 3. 4, 8 came here. 5, 10, 2, 1 is there. So 10 is there. So it's called max pooling. 6, 7, 2, 15 is there. So it's called max pooling. Then we'll be going to give the indices 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1 and all. Then accordingly we're going to place the unpooling. We have done the pooling. We'll go back again with the help of the padding. And how it will look like our unit model. We're going to skip sometime. It's going to skip, again came, then it's going to again fully going to follow all the methods and all. We can see the conversation that like diary that the going to be a max pooling. This is arrow is the copy. Then up convolutional, that's going to be up convolutional, like it's called up sampling. Whatever I explained so that the same thing are here only. Then the convolutional we have is the output. Okay. So this architecture actually for the what unit. Then what we have the
Hello, sir.
yeah
Hello.
yeah in doubt is there.
Sir, I just want to know how this unpulling is done. Is it with respect to the indices we have defined over there? The
Sorry.
positions of till max pulling it's okay,
Yeah.
but how this unpulling is done, sir?
Unpulling is something that we are giving the similar to the padding. Let's say we were having something was there, but it was the imbalance was there, and we have given the zero here, zero here, zero here. Similar way here also same concept is there. Like as we can't go back to the our that the original one. So what we'll do, we're going to give the padding, like similar to the padding only, but we'll term the name as a what we can say that is unpulling. So for that we have to define that is indices like one. It's going to same for the like that's for the diagonal and all. It will be 0, 0 or 0, 1 because we have only two. So that the two like a two class is there. We all know that 1, 1 both are true and predictor is same. 0, 1.
Uh, are, is for
Sorry.
9 and 15. Then how these are positioned actually? What logic is used?
Positioning, you can do randomization. We'll be having in that if you give in the matter code, so they'll do by their own. We don't have any like like what I can I say? Let's say 0, 0, 0, 9. So in that also, if you go with the max pooling, so we'll get 9 only. Here also, yeah, no, I'll tell you just 1 minute now. This so this 9 position we have, this 9 position we have fixed it out, but we don't know 5, 6. We can't go back. So simply we'll keep the 0, 0, 0 here. Fine. Then after the 8 position we know here, 8 position we know here. This one we can't go back. So unpulling, so simply we'll keep the padding as a 0, 0, 0. Is it? Then after 10 position we know here, 0 here, 0 here, 0 here, then 0, 0. I think it's clear now. The positions of that 8, 9, 10, 15.
So indices have come, indices, no? Indices of maximum value. How is that 1 1 has come?
It's a 1 1 like we have defined. It's 1 1 and all that we have defined actually.
Okay. But
It can be of 1 1.
you are
It can
calling
be
it
of
indices, right?
like it's a class. We can say class. We can say either 1 1, 0, 0. But the thing is that padding we have done for that.
So four possibilities are there.
Yeah,
But where do you keep each one? How? Why? 1 1. Why it is in the first place?
1 1. As we know that if you see the confusion matrix, it's going to be a predicted one. It's going to be true. So if it is that one predicted also true also, it will become the 1 1 for both of them. It's going to same here 0 1 or 1 0, but here 0 0. So that we have done like either 0 0, either 0 0 1, 0 1. So it's something. Uh, this one will be 0 1. So it's become the 1 0. Okay.
Okay.
Sir, is it the row or column number for 2 cross 2 max pooling? I think it is showing that.
Sorry.
I think 1 1 is showing max pooling of 2 cross 2 for this image, whatever the you're showing 6, 5, 8, 9. So the position will be 1 1. So first row and first column. So the position 9 is positioned there.
Yeah.
Similarly for 0 0 for 2 cross 2 max pooling. So here it
Yeah,
was
similar
0.
way it will come. Similar way it will come because it will be the max pooling only. But the only thing is that the positioning will come wherever the because of the max pooling that so that the position came, and this is going to be from that indices only. It came that if you're going to 2 by 2 that multiplications,
Yes, sir.
Hmm.
Sir, this concept is clear, but if we have more number of like, it is clear because it is by two we have considered. Okay, sir.
Yeah,
So can we increase the bits of indexing?
I didn't get
Like
it.
if huh, uh, pooling we have taken 2 by 2 we are doing it, sir. We are taking maximum value.
Yeah.
So that's why according to that 2 by 2 we had assigned 0, 0, 0, 1, 1, 0 and 1, 1.
Uh-huh.
So can we increase the size actually for the larger classification
Yeah, we can
or
go for the if we have the multiple class. Let's say I have 3 classes there, so I can go with the 0, 1, 2, or even 3 by 3. That matrix can go. 4 by 4 can also go, but it will be the it will going to complicate. So that's why in the starting we told like we'll go for the binary classification, multi-class classification. So we have to improve like increase the size of the what you can say class actually.
okay, okay, sir. Thank you. Thank you.
I think we are a bit behind. We have to go a bit fast. Okay, so this is the whole about that one. So then we have one more thing like called DenseNet. DenseNet is actually is going to adapt for the semantic segmentation primarily through the FCN only, but it's going to be 100 layer tiramisu. It's one term, one sentence so they gave. This approach actually going to extend the standard of the dissect into the encoder framework. It's a pixel-wise classification. Instead of we are going with the class-wise, it's a pixel-wise classification also we can do. So it's an input image, convolution, then the dense block. From here also we can go to the our softmax layer, argomax layer and map. Further we can do the transition down also and then dense block, then come back here. It's something like we are going to transitioning the pixel to the lower, or either it's a getting the maximum information from the like an image we can get it out. Pixel wise information that the as we know all know that the starting we have much more feature maps will be there. Once we do the like convolution and all, so it become the downsampling. So if you're going to downsampling, so it's a feature map. If you go with the like dense block, so we are going much deeper. We are going based upon the pixel level. So that's the whole idea of to get the what we can say dense net FC, fully convolutional dense net convolutional. So all things are same. Only thing we have to another parameter like that's one encoder all are there. But the thing is that we can get the pixel wise like much detailed information we are getting. So what are the things will look like? Architecture that we have seen the dense block, and we have the encoder and decoder also. Then we have the skip connections also we are having. Then how it's going to help it out? It's going to give the parameter efficiency like F9 F dense net typically achieve state of the art with significantly few parameter up to 10 times of the less whatever we have the F segnet and FCN, and they're going to give the refined boundary by that we know like it's going to denser, so they will going to have much more defined boundary, so that we'll be able to help in the skip connection, so that they will going to lead to sharper object boundary in the semantic mapping. So it means we are going to divide much more boundary. So it will help for the unit classification unit. So we can get the better results. And each layer receive the dice that the supervision from the loss function and shortcut the path and all. So it's something we are going much more deeper and all. It's a extension of what we have segnet and unit and all. Okay, so here the only things will comes into the picture is the dense, and that too with the at the pixel level. We'll be having the class level, the feature map will be there. Along with that, we'll be having the pixel level also. Then one more thing comes into the picture, like let's say I have run the first code there. So whether how it going to look like whether that parameter is going to optimize or not. Let's say our like some parameters are there. Will you have the parameters of that's called the number of that the hidden layer, number of unit per layer, activation functions and all. So if the results came in our ways, it's okay. That's our going that parameter is going to optimize. But once we have the biometric application, that the some applications of the result or accuracy will not going to get proper way. So if we are going to set the wrong parameter, it's going to drastically affect the performance of the network. So let's say we have to define the 0.0005 of learning that we define 10. So that whatever the let's say we got that the 90% for this, and if you're going to put for the 10, it's going to drastically for the 40% of the accuracy will comes into picture. So means if we don't give the correct parameter for the correct model, we are going to face the what I can say like drastic change in the performance. So it's going to make the training of the neural that the network extremely difficult and all. So again, the thing that so then how can we improve the what you can say, parameter, optimized parameters. First one is the grid search. Grid search parameter. So what they will do for each grid, they're going to train the model. So train the network with the each possible configuration of the hyperparameter. So what will happen in that case? In that case, that the kind of that the traffic so parameter is going to increase exponentially, and they will go for each second, third, fourth, five, sixth, each and all. So what will happen? So for that parameter will be going to be like increase the exponentially, and this is going to feasible only for a small data set, not for the large data set. So the second one, what we have, it's a random search. So rather than training all possible configuration, we are going to network on the only subset. Let's say I'll go for the first one. So as we know that so there's chances that we'll get this subnet, and this might have same properties. So second can go here, third can go here. So we'll go on the only few, and then choice of the configuration to be trained randomly on the only best configuration is going to retain. So they're going to do randomly, and then we're going to select it. Then the third one, what we have, third one we will do with the let's say one ANN model or CNN model, we took number of hidden input and all 64. And second one, what we have done, we have for this particular we got 65%. We increased 100, it become 82%. Then again we went to 200, it became 84%. So it might be sometime okay, but the thing is that this is not going to be a reliable always for a simple model and all that we can change around and all. But the thing is that to get better that so that the parameter optimization and all, and in the paper also so that reviewer will ask whether you have done the like grid search or the random search, or maybe we have Bayesian search also there. Here Bayesian search is also there. They are going to use probabilistic model to predict which parameter is going to perform based on the past result. So it means in that case we'll get the typically fast convergence result. Then we have that meta heuristic evaluation, that's the GA will be the genetic algorithm is there, particle swim optimization is there, then the gray wolf is there. So this is going to be advanced one, so that will not go much into that advanced hyperparameter optimization. So one, two, three. Then we have the and two. So that is the people like for simple problem. But if you want to make some impact and all based upon the genetic algorithm, that will, like it will become mutation rate and all. So it become again another type of what you can say like complex model and all. So these are some methods that we have to follow it up for the best parameter to get it out. Then after one more things, what we have is the transfer learning. Transfer learning, anyone have the idea like transfer learning is something that we are having one model that already existing. So we are going to use that parameter for the another model. So how it's going to work it out, I'll tell. Transfer learning in the CNN is actually a technique that involves reusing a pre-trained model as a straight pointed new task. Like we'll be going to run on the simple one model on the basic feature, or maybe the low class feature. We'll be having that feature, so that model I'm going to use it out for the high class feature for the further. So it's going to save our time or the complexity also. So means remove the classification layer in the network, forward pass method, then so then after second one step will be in that also SVM LR we can use it out, no issue. Then we can go with the initiate a network with the pre-trained weights. Like we have whatever we got from the previous trained model, we're going to use it out. Then the modify the classification layer from the 1000 even to the number of classes in the new data sets. It's a fix will be there. Let's say for this number of data sets, we're going to increase. So train the network with random initialization that ligation. So this will call with transfer learning will call. So it means something what we were having a existing model. Let's say a person for the bike, it was the basic model something that Rajdoot was there. Then came across something. So it was the something concept we already know. We are just making the improvement. We are going to whatever the concept we have, we are going to use for the another things alone. Let's say one invention I have done. I'll be going to use that I am the patentee. Other are going to use my model or my that is the findings for their product or not. So similar way that the heroes. So that's how it will going to work it out. In that also, say the senior is going to learn early layer. It's going to generic low level feature like edge, curve, line and all. Middle layer, basic feature like something like a object or something with. Then the later layer, exactly high level features and all. So first, second, third, first one we will use for this. Once you got this one, we'll go to use for the last layer. So we have different how it's going to work it out. I told like it's going to be a train select a scene architecture for the baseline. We have used this VGG that residual net inception in the previous class and all. Then after modify the architecture, remove the original block, and then add whatever the task what we have. Add the custom layer also. Freeze the base layer. We have to freeze the first one. Then after train the new layer. Then we'll get the fine tuning will be the our optimal results will be there. Okay. So scenario one, small data set. Similarly, of the data with the image data going to the train initially train only deeper layer. Example classification of the medical image. Second scenario, a small data set similarly of the data with the image net high. Like something will take small. Let's say this is going to a small data set will take and data with the image net look low, then high. Change in number of people into the output layer from the 1,000 to appropriate number. It's an exact number. I'm not saying it's just a way, different that the scenario we can do around or we can play around actually. Then we have the scenario three, large data, low data similarity with the image data case. So this is the third case we have. So this is the whole things till now we have learned. So today that the theory part is completed. What we have learned, we have learned like one code like how the full architecture was learned. Then semantic segmentation we have learned. We have changed checked with the that instance segmentations also and popnetic segmentation also. Then we went to the fully connected layer, like how it went and all. We have in that also check unit. We have check, and then we have check deep lab. We have check. We have check around one PPSN. We have check around. Then came across the hyperparameter optimization. We have grid. Then we have that random is there. Then we had the hand tuning is there. Then we were having probabilistic where the Bayesian was there. Then we came to the finally for the transfer learning. So now we close with the CNN. Now we'll solve some problem and all. And along with that, if you have some problem also, we can see them. So first one is that what is the technique? Which technique was mentioned as a hyperparameter optimization method that explore all possible combination parameters? And anyone tell?
Bayesian optimization.
No. So they're going to explore all means all grid. So
Great
it's a
search.
grid, na? Bayesian is based upon the probabilistic.
Yes, grid search.
Yeah. And this is going to random search, like we'll take one here, one here, one here. And then optimized model will come, we're going to output. Fine tuning will be going to do with the play with the number of neurons. So second option, grid search. So it's just a search technique that systematically evaluate all possible combination of the parameter. If you are learning rate of this much, so batch size of this much, so they'll play all nine combinations of this parameter. Other methods like random search for while Bayesian for the evaluation for the guide search, hand tuning is going to manage a different with our expertise. What is the main challenges when using CNN for the brain tumor simulation from the MRI scans? Can anyone tell? I have to discuss about the MRI. We have the brain is there. Let's say, okay, wait. So this is the brain. Okay. So there is for the low resolution, this is not going to concern. We have the very high sophisticated machines are there. Lack of compression resource, that's also we don't have the what I can say that constraint in that. Availability of the level data, this also we don't have the concern because people can work on the super unsupervised learning also. Is it? So I told for a brain this much, so tumor will be this much will be there. So means class imbalance, chances of the imbalance will be the more. Is it? Because class imbalance with the tumor occupying less than the 5% of the brain volume only. So this is it. Is it correct?
Yes, sir.
Because I gave the example before. MRI will be like the tumor and all. It's not going to be come all alone directly in the brain or maybe lungs. It will come like very small. Then we can get to the MRI. MRI is going to high precision device. It's going to occupy 1%, 0.5%. I just told like it's a 5% of the brain volume. So means
Sir, is it due to accuracy of CNN that
so
5% they cannot detect?
sorry.
Is it due to accuracy of CNN network that they cannot detect 5%
Like just
brain
see
volume?
accuracy. We are not talking about full CNN. CNN like what is mentioned when like it's a the problem is the class imbalance. CNN, it can be have sophisticated like we can do that improved CNN that model and all we can write. Okay, we can improve the going to be a model, but if we check at the basic level or fundamental level, so the so main challenge is the class imbalance, and CNN doesn't like it doesn't handle the well when the class imbalance is there. Okay.
Okay, sir.
So because it becomes the highly skewed distribution between the tumor and the that's going to non-tumor class now. So it's going to imbalance and it will lead to the training issue in the neural network. So in the unit architecture, we have discussed the unit architecture. What is the purpose of the skin connection? Skip connection. Can anyone tell?
C.
To combine the low level, high feature realization. Anyone? Others? Speed up will be not there. Prevent overfitting will be not there. It's going to combine only. What they will do? They are going to combine only. The encoder extract high level feature semantic. Decoder, it's going to do the but need detailed information. Skip connection directly connect the corresponding layer between the encoder and decoder. So it's going to combine low level with the high level, low feature resolution. So this actually that our segmentation part is that there is no point of going to reduce the feature. We are not doing the transfer channel. What we are doing the first one, first half encoder downsampling. Then what we have, we are going to use the one by one, and we'll do the in the decoder. We are doing the upsampling. Whatever the feature was there 4096, it's supposed to come here also 4096. So means there is no point of reduce the parameters and all. So this is the correct option. Is it correct? When we are going to use the fully CNN network semantic segmentation, what operation is performed on the final feature maps of the to determine the pixel class. I told like in the case of CNN, we can use the softmax. ReLU is actually for the convolutional layer. Sigmoid is the non-linear. So we are going to use which one? Argmax. Is it? Argument of max.
Yes. Yes.
It's correct?
Yes. Correct. Max is correct.
Yeah. So in filling out like so we're going to use what? Softmax is going to apply for the convert to logistic probability. But the argmax is used to select the class with the highest probability. It's the argmax is something called highest class. So we are going to use argmax fully. Why is transfer learning particularly useful for the medical image task? Again, some difficult question. Can you just tell? Medical data are often limited inside. No, we have plenty of the data. Is there? Is it?
C is
Medical
answer.
images are easier to classify than the natural images. No, people. Even natural image, but it eliminate the data. I'm going to say no. So it means pre-trained network. We know the pattern of any specific disease, so that we can use for the our future also. Is it?
Yes. Yes.
So means we know the for a one disease we know the particular pattern we know. So we have trained for that. So the same thing can be transferred to the any other model. So we don't need to go again from the scratch. Is it?
Yes.
Yeah. What is the what method we are going to use to match intensity distribution across the MRI image from the different center? It's actually yeah, it's going to histogram only. This one will talk in the next class, like for the MRI application CNN, and it's actually so for different one so that intensity value and all. So leading to intensity model, so we're going to use the histogram. Histogram is going to give the intensity distribution. What will happen? So they will give it so along with the one image will give the one intensity, and we know the level also, so we can get the variations also. So that's why we'll see around. So this is actually application based also. So the correct option is the histogram. Gamma correction is actually it's going to different one. Contrast enhancement is something that we are playing with the picture itself. Gamma correction is something we are adding some weights and all. So that we are not doing as such. Min max normalization also we are not doing as such. Like it's a so we have the histogram matching itself because the image have the different intensity. So we can see the variation with the intensity. So we should not do the any of the corrections, any of the normalization, any of the enhancement and all. Why? Because we can't manipulate or we can't do the interpolation for the already medical devices or that is a MRI. We can't do. Okay. What is the main disadvantage of the grid search for the hyperparameter optimization as the number of parameters increases? But what is that? It becomes that's called less accurate. No, it becomes maybe sometime a good result they'll give. It requires more memory as we don't have sometimes the constraint. We have the supercomputer, we don't have the constraint also. So no issue. It cannot handle current, but it can handle because it's a class problem. The thing is that number of experiment is going to increase exponentially. So that is the main problem because they have to go through the each grid. Yeah, that is correct now.
Yes. 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 All combinations they have to go through.
Yeah, yeah. What does a softmax layer do in a neural network? They are going to normalize. No, normalization is different. Convert raw output source into the probability. Yes, they're going to convert. That the reduce the overfitting, they will not do it. Speed of the conversion, they will not do it. That's the only things they will do. So they're going to convert a function or output scores into the 0 to 1. It's a probability distributions actually. Correct? Huh?
Yes.
We have the what feature of the dense net help with the information flow in the deep network?
The direct connections from each layer to all
All
subsequent.
subsequent layer. Residual, it's not the ResNet. It's a combination of that. Wider layer with the more filter, no, we're not playing with that. Dropout, we're not playing with that. So it's going to directly connection with the from the each layer to the all so because they're going to work independently with the all subsequent layer. Is it? In the ResNet skip connection, in the traditional shader, it's going to connect with the only left layer only. Okay, so that's all for today. How was the session like today? Can you give some feedback?
Sir, it was interesting. Thank you so much.
So thank you, sir. Thank you.
Yeah, sure.
Thank
If you
you.
have some doubt and all, that you can ask in the coming class.
Thank you for the explanation and
Thank you.
patience. We have
Okay, thank you, sir.
Thanks.